That brings me to the fourth application. And this is really a different one. So it's about an intervention study. So it's a randomized controlled trial. And so we can assign people to different treatments, gather ESM data, and see whether, for instance, the means are different across the two groups, or the variances, or the dynamics, the autoregression, or certain cross-legged relationships. Here I'm focusing on a data set from Nicole Geschwind, and it's a negative affect that I'm focusing on, and it's individuals who have a history of depression but are currently not depressed. But as you know, as you probably know, there's a big chance of relapse when you've had depression. So there were actually two periods of ESM data collection. So it's a bit like the measurement burst design idea that Nesselrode proposed. So there's ESM data before the intervention. Then people were randomly assigned to either treatment or no treatment. And then there was ESM after this period. And the treatment consisted of mindfulness training, which is a training that's been developed and used a lot to make sure that people who have been depressed do not fall back into depression once they've recovered. And it's very promising. So it's interesting, this data setup, to see if we can see whether the dynamics of their affect regulation change as a result of the intervention. And I'm actually focusing on different variables than what they were doing in the paper. So I'm not, in that sense, contradicting their results. They found different results than what I find here. But, and that could be, because of slightly different approach or different variables or, So it's more an illustrative example. So the data, the way they would be set up for a single individual here, we have the first phase, so the pre-measurements, and then the post-measurement or the post-intervention phase. So there's two phases, phase 1 and phase 2, and then within each phase there's repeated measures. Here there's like nicely follow, they nicely follow up. There's no missing data, but of course in practice that's different. And then there is some Y variable that was measured. So it's just one variable. Now we could do stuff with DSEM, creating dummy variables for the phase and then have complicated interaction terms. But especially with the decomposition, this is not so helpful. Because then for the decomposition into within and between, we would decompose, we can just get one mean that represents the mean in the reference period, so that's like prior to treatment, but we wouldn't have like the mean after the treatment. That would be a product of something with a dummy variable. And so I just was thinking about this and I thought like, oh, this is going to be horrible. And then with the autoregressive parameter, I want to see whether it changes over time. And then I thought like, well, maybe another way to do it is just to make two new variables. So I'm going to have a variable that I call y1, which is just the y variable during the first phase. And there's no observations during the second phase for this variable. And then I'm going to have a second variable that I call y2, and it just has the y observations for the second phase. And so there's missings for the first phase. So now if we specify, for instance, an AR1 model, we can do it separately for both variables. And this one would be centered with the mean of the person prior to the treatment, and this one would be centered with the mean of the person after the treatment. And I would have two latent variables at the between person level, one representing the mean prior to treatment and one representing the mean after treatment. So I thought this was a really nice way to do it. I emailed this to Bengt and Theomir. I said, like, does this make sense? And then Theomir said, sure, Ellen, we do this all the time. So I was like, oh, well, okay. It was a good idea, yeah. You wouldn't do it all the time if it wasn't a good idea, right? It was? No, we have to tell telomere. Anyways, so, all right, where am I? Treatment effect on the within-person mean. So first, we're not doing anything with dynamics, no lagged relationships, just looking at, are these means different or not? So we have two variables, NA1, so negative affect prior to the intervention, and NA2. And we have two groups, people that are going to have the treatment, or had the treatment at some point, and people who don't. So that's going to be a dummy variable. In the decomposition, it's just, the decomposition is just as it always is. So a variable is split up in a mean for that person, and a temporary deviation from that mean, which ends up in the between part. In the within part, and this ends up in the between part. At the between person level, I'm specifying the mean, regressing it on the dummy variable group. So for the mean prior to treatment, I don't expect group to have an effect, right? Because that would mean that randomly assigning people to the different conditions was not done properly. There shouldn't be prior differences in the means between the people in the different treatment groups. For the mean, the individual mean after the treatment, of course I want to include group as a possible predictor, but I am also regressing it here on the individual's mean prior to the treatment. And I'm not just regressing it, I'm fixing the regression coefficient to 1. Yeah? And this, I'm doing this because then I can actually rewrite it like this. So I can subtract the prior mean on both sides of the equation. So I get the difference on the left-hand side. So it's the change in the mean. It's the change in the mean between before and after. And it's a function of the treatment. That's what we have here. And there is an intercept here. It's gamma 1, 0, same as the gamma 1, 0 here. And that would just be the effect of time, right? So if this was different from 0, it would imply there is a difference between the two means, even if you were not in the treatment group. So that would be the effect of time. Yeah. So to specify this model, this is how we do it. So at the within-person level, I have two variables. By default, Mplus will look for a correlation between those two variables. But I know that if one variable was observed, the other one is missing, because that's exactly how I made them. So that's why I fix the covariance here to 0, just not to make Mplus confused. I'm not sure what would happen if I don't do this. I didn't try it. I don't know why. But I thought, I'll just help. I'll help the program. Yeah, not identified. That's what I was thinking. I'll just keep on. But maybe, it wouldn't have a problem. I don't know. So, but that's why I'm doing this. That's because if you have NA1, then you don't have NA2 at that same occasion. It's impossible. Because one is for phase 1 and the other one is for phase 2. At the between-person level, I regress the mean of NA1, so that is mu NA for person I, on group. And NA2, so that's the mean mu NA2 on the mean for the first phase, so that's mu NA1. Fix this, this regression coefficient to 1, and then I also regress it on group. And then I allow the residuals to be correlated. So the residuals of those regressions, if you go back here, so it's these residuals here. Yeah. All right. So this is what we get at the within-person level. We see that I fixed the covariance to 0 here, so it's not being estimated. These are the variances. So this is already interesting to see, I think, is that the within-person variance seems to decrease, between the prior and the post-phase. At the between-person level, we see NA1 on group. So this is the mean of negative affect during the first phase regressed on group. That's where we expect to find a 0 coefficient, because otherwise random assignment would not have been correct, right? So we don't expect differences here. I will have to where is it? Yeah, if you compare it to slide 55, it would be this parameter here. So gamma 0, 1. And that's an initial difference between the groups, so you don't expect this to be different from 0. And it's not. As you can see, the credible interval contains 0, so there's no evidence that there were differences between the two groups prior to the intervention. And then we regress the mean of the individual's means, or the within-person means, on negative affect after the intervention. We regress it on their mean prior to intervention, but that's fixed to 1, as I said before. So I can think of it, the other variable, as predicting the difference. So group has a negative effect on the change. And it means that for the people who were in the treatment group, they have a score 1, their negative affect went down. Their average negative affect went down compared to what it was before, in comparison to the other group that was not treated. And we see that there is evidence that this is really an effect. NA intercept here of NA1 is just the overall, the group mean prior to the intervention. So that's not really an interesting thing in itself unless you really know the scale. Negative affect, the intercept of negative affect for the second phase, this one here, that would be the time effect. So that would be this parameter here, the gamma 1, 0. If you rewrite it like this, you see it's the effect of time for the change. Does that make sense? So we see in this initial analysis, we see there's no there's no differences between the groups prior to the intervention. We see that after the intervention, the treatment group has a lower mean on negative affect. So the intervention was successful in decreasing negative affect. And we see there was no effect of time. So this effect did not occur for the control group. Okay, now we want to extend the model with autoregression, because actually I was super excited about this idea, that maybe the autoregressive parameter will also change as a result of mindfulness, because I thought a part of the idea of mindfulness is that you stay in the moment rather than to ruminate about what happened and worry about what's going to happen, and where you basically keep on perpetuating your negative affect. You are supposed to stay in the moment, So that might decrease the autoregressive parameter. Yeah? So we have the model prior and post to treatment. And then at the between-person level, we now have, for the prior part, we have mu1 from the decomposition. Again, we can regress it on group to see whether there were prior differences between the groups. And also the autoregressive parameter, whether there were no initial differences in autoregression between the two groups. So we expect those parameters here to be 0, right? And then for the post-treatment phase, we have the mean of this, of the variable, the original variable, so from the decomposition, and then the random slope here, so the autoregressive parameter. So mu2 and phi2, they are regressed on their pre-treatment counterpart, so to speak, again with setting those regression coefficients to 1, and then regressed on group as well, such that if I subtract mu1 here from both sides, I get the change in mean as a function of group. And I do the same for the phi parameter. I subtract phi1 from both sides. I get the change in the autoregressive parameter as a function of group. And then the intercepts here, which is the same as the intercepts here, they would represent just an effect of time on those parameters. And these are the results. So we see phi2 on phi1, that one was fixed to 1. Phi1 on group. So that's, are there initial differences in the autoregressive parameter between the two groups? And this is not different from 0, so that's encouraging. There were no initial differences in the autoregressive parameter. Phi2 on group, remember that because we include this as well, it's the change in the phi parameter regressed on group. And we see there is, that 0 is in this interval, so there's no evidence that the change in the autoregressive parameter was a function of treatment. So that was disappointing for me, from a clinical background, but anyway, that's empirical data. And then we had initial differences in the mean of negative effects. That's what we had before also, and we see 0 is not in the credible interval, so there's no evidence for initial differences in the mean of negative effect between the treatment group and the control group. And then we have the mean of negative effect in the post-treatment phase, regressed on the one pre-treatment phase. That one was fixed to 1, so that we can interpret this as predicting the difference, and that one is still significant like it was before, a negative effect. So it means that if you were in the treatment group, there's the prediction is you have a lower mean after the treatment, in comparison to people who were not in the treatment group. Yes, and then we have the intercepts. First one is just like, is the mean during the pre-treatment phase different from 0? It's not so interesting. This one would be the time effect on the mean. We see it's not significant. This one is the intercept for the autoregressive parameter prior to treatment. It's just the average phi parameter across individuals. So that's different from 0. It just means that there is carryover from one occasion to the next for these people. And this one is the interesting one. So we see that phi2, the intercept, is actually significant, different. So it differs from 0. So what is this intercept here, this phi2 here? If we go back, it's this one here. It's what we refer to as gamma 30. It's the intercept, you can look at it here. It's the intercept of phi2. And if we look in this equation, I find it clearer, it's the effect of time on the autoregression. So if you were not in the treatment group, you have a 0 score here, this drops out, so there's an average time effect. It's negative, so it seems that there is a drop in autoregression between pre-treatment and post-treatment that's just related to time and not related to treatment. So that's the result. I don't like it, but that's what it is. This says all effects random. Yeah. So here I allow everything to have a random part. Yeah. So then, I maybe shouldn't say this, but you know the statement like torture the data until they confess. That's sort of. I was thinking like, oh well, what other model could I do that's like closely related and maybe makes more sense actually. So I thought maybe I should just fix this residual variance here to 0. So I'm saying, sure, there can be individual differences in the phi parameter, but those individual differences do not then randomly change. So they might change because of time, they might change because of treatment, that's of course, it's already there in the beginning. So they might change because of time, that's in the intercept, but they don't change differently for different people. That was the idea. And it was also, sort of to to defend my case a little bit here. I was, thinking like, okay, we have so many random effects and then everything correlated with everything and everything. You just get so many parameters. So maybe I should just try to make a simpler model. Anyway, so that's what I did. And then, what I add to the code is phi2 at 0. So that's just saying, whoops, the residual variance of phi2, so that's this part here, this variance is 0, the variance of this part. All right. So that's what I did. And now what we see is suddenly phi2 regressed on group now is significant, whereas the intercept of phi2, so the time effect, is no longer there. I think this is a case where you should not be happy, actually. Because we don't want sort of minor changes to the model to make this big of a difference. Like, does phi change? Does the autoregression change because of time, or does it change because of treatment? It's quite a different thing, right? So, and one of the things when I was looking into this, just coincidentally, but these things seem to happen all the time, coincidentally, but I saw this discussion somewhere on the internet about multi-level models and whether you include all the random effects or not. It was related to a paper that was retracted because after they added the random effect, the main results from the paper no longer held, for the fixed effect. But there is a paper by Barr, so B-A-R-R, and others from 2013. Anyone here knows it? So they do a simulation study and they show that if there actually are random effects and you don't include them in your model, then your type 1 error for the fixed effects increases. So basically they are saying you should always include all the random effects. This slide is wrong, the previous slide is better. So that's the bottom line then. I don't know, it's just like something that I think, we need to do a lot more research in this area to find out how to approach these kind of problems. But this is just to make you aware that these things might happen. Like you change something and then there might be changes in other parts of your model. Okay. Then another way to extend this model is by including a level 1 predictor. So it's a level 1 predictor. And again, I have it for the two phases, so pre-treatment phase and post-treatment phase. It was one variable to begin with, but then I made it into 2 variables. And it indicates whether something emotionally charged happens since the previous beep. So as DSEM data, you ask people at random time points during the day, how are you feeling right now in terms of negative affect? And did something like positive or negative happen since the previous beep? So in a way, this variable, even though you measure it at the same time, is referring to a lagged relationship. Do you see this? It's like about the entire episode or like the period before this beep. So that's why I think it makes sense to not use lagged versions of those variables, but just the concurrent version as a predictor of negative affect. If you have a positive score on this variable, then a pleasant event occurred. If you have a negative score, then something unpleasant happens, and it's more or less a continuous scale. So the model that we're going to use is this. So we have negative affect regressed on negative affect itself at the previous time point, plus the unpleasant or pleasant events. That's what the U and the P stand for. I always forget. The unpleasant versus the pleasant events. It's like the entire range. And so as you can see, now we have T here, not T minus 1. So it's not a lagged, the variable is not lagged. But because it's the question is referring to the period prior to the beep, it's in its measure already lagged to some extent. So we have the phi 1 and phi 2. They represent the autoregression or inertia or carryover of negative affect. And then we have beta 1 and beta 2. They can also be allowed to be random. And they represent a person's reactivity or sensitivity, right? So now we actually have a measure of something that used to be just ending up in the innovation term. It's like whether something pleasant or unpleasant happened. Now we have a measure of this, and now we can see whether individuals differ in how much they respond to this, right? So this is something that especially Marieke Wiggers and other people from her group have been studying a lot, is this sensitivity or reactivity. And also when they are studying positive affect and the effect of positive events on positive affect, it's referred to as reward experience. And they found that, for instance, after treatment for depression, people who respond better to the treatment also increase in their reward experience. So their moods are uplifted more when something positive happens than before they were treated, for instance. So it seems to be an important thing. Yes, so this is important. We now have concurrent regressions. So if the variable measured at the same time point as the outcome, rather than only lagged predictors. So group is the predictor at the between level. So we regress those prior or the pre-treatment mean, autoregressive parameter, and reactivity on group. And we expect group not to be significant here. And then we also do the same thing as we did before for the change in the mean, the change in the autoregression, and the change in the reactivity as a function of group. And then you can think of the intercepts as just the effect of time on those quantities. Now, to do this, we run into a little bit of a problem, because the predictor has missing values. But now it's not a lagged predictor anymore. It's a concurrent predictor. And then, if we don't do anything, Mplus will just delete the cases where the predictor is missing. So we don't want this. So we have to make those variables part of the model. And another issue, now I have to think. There was another issue. This is terrible. All right, yes. Tiomir, can you help me out here? There was a problem. So we have the predictors. They are concurrent predictors. We want to have the decomposition into within and between. But why was it not possible for concurrent variables with missings? Oh, that was it, yes, that's it. Thank you, Bengt. Sorry. Yeah. Yes, that's the point. Oh, yes, yes. We have random slopes here, and that's not allowed when you have concurrent predictors with missing values. Is that it? Yes, yes. Not yet. We don't have it yet, yes, but Tiomir will solve it. Unless we, decide that he has to solve something else first. I have a few things on my wish list. So, anyway, so that's why instead of being able, so that's why instead of saying, this is just part of the model, blah blah blah, I'm defining these variables just as purely within variables, and then saying I want to use group mean centering for those variables. So this is now, instead of doing the latent decomposition as we are doing so far for the outcome variables, it will use the sample mean to center those variables. Very boring, but that's how we have to do it. And so we also will not have the means, the individual means of those variables at the between person level. Because they are defined as within person variables, they do not end up at the between person level. The means are not there. Yeah? They were just subtracted, and then the variables only exist at the within person level. So it's a concession we have to make. Okay. So here, let me see, we have so here we have the model again. So we have the part for the autoregression, pre-treatment phase, the reactivity pre-treatment phase, and then autoregression post-treatment phase, reactivity post-treatment phase. Then we specify that the pre-treatment variables and the post-treatment variables are not correlated in any way, or they have a correlation of 0. And I do this, to make sure that it will not delete cases with missing values on these variables. And then between, we just have the random effects. So the mean of negative effect, the random slope phi, and then the beta parameter. So this is the first part where we see, are there initial differences between the groups on the mean, the phi parameter, or the beta parameter. And then we do it also for the post-treatment. We regress them on the pre-treatment versions with the regression coefficient fixed to 1, and then also on the group variable. So it's just basically the same thing, but just extended with one more term. And these are the results. And basically, we see there's only one thing here. Yeah. So we see that the mean of negative effect, or the change in this, was actually a function of group. Again, a negative effect of group. So it means that if you were in the treatment group, you had a lower mean on negative effect after the treatment, whereas for the people in the control group, the mean did not change, because there's no time effect. I think, where is that? Let me see. Oh, the time effect is in the second slide. Sorry. But for all the other things we see, there's no effect of group. If we look at the time effects, we see them in the intercepts. So for NA2, we see there's no change in the mean of negative effect as a result of time. For the beta parameter, we see there is an effect of time. You see it. I'm looking at the wrong line. That's just saying, were they different from 0 prior to treatments? And they are, but that's not something super special. And then we see that there's no effect of time for the autoregressive, or the change in the autoregressive parameter, nor for the change in the reactivity. So it's a little bit boring. But that's what it is. Okay. And then we can also, of course, look at standardized regression parameters. So the autoregressive one, and also the beta parameter, and look at how they have work out, at the pre-treatment and post-treatment phase. And the nice thing is that the standardized parameters for the post-treatment phase will actually be the whole thing. It will not just be about the residual. So then you can look at whether the effects change. And of course, here we don't expect to see much change. But if treatment or time had a significant effect, then you might see more interesting changes here also.